So we're going to get ready to go through and do a practice exam. Now, practice is really good. It helps us understand concepts, see where we know what's going on, and see where we don't know what's going on so that we can fix that. Now, it does not mean that these are the problems. They're not. But they will give you an idea of the types of problems you might have and some sense of the level of difficulty you might encounter. I will say I am probably slightly biased. I throw in a little bit more interesting, but not wildly more interesting problems. And so this is a good way for you to gauge your preparation. So we're going to have fun. 10 problems. We have 6 multiple choice and 4 long answers. All right, let's get going. Number 1. Find div. Now, div is short for divergence, and it gives us a vector valued function. X squared y, comma, 3x plus yz cubed, comma, 4z plus xy. Now, what do? Well, you hopefully know what div is, but even if you don't, you have a formula sheet. And pro tip, that has a lot of really good information, like a lot of really good information. And so make sure you're ready. Now, what is div? Well, div, one way you can say, that's our del dot, our x squared y, 3x plus y, z cubed, and 4z plus xy. There we go. All right. And del, remember, this is our collection of partial derivatives. So partial x, partial y, partial z. So now, well, that says what? You should have partial x of the first term, x squared y, plus partial y of the second term, 3x plus y z cubed, and plus partial z of the third term, 4z plus xy. These are all straightforward partial derivatives. What do we get? Well, we get 2xy from the first. Here, that goes away. And then we get plus z cubed from the second. And then from the last one, that part, the xy, goes away completely. Derivative of 4z with respect to z is 4. So that's what we're looking for. D. Answer is D. And there you go. Yeah, they can be that straightforward. And I will say, one of the goals of multiple choice is not to have lots of intricate steps, but usually just says, okay, can you do an operation? Do you know what this means? Do you know how to set things up? Now, I do encourage you to make sure you have the right concepts, because even before you started, you could have narrowed this down really quick. Well, what do I mean? Well, namely, you have some nice facts. There's 3 types of ways that we use this del operator. So we have what we call del f, or that's the gradient of f. And what happens is here, this sends a scalar function to a vector function. We have del dot capital F, so I'm using capital F for vector function. This is the one we just did, that's our divergence of f. And what does that do? Well, that sends a vector valued function to a scalar valued function. So in other words, you start with something which is a vector valued function. You have to get something which is not a vector valued function. It's a normal function, which says A, B, and C would automatically be out because they're the wrong type of function. So even if nothing else, you can knock out some options. One other thing, which might or might not show up on this practice or on the exam, is the curl. Now, I will say it's definitely going to come for the final, because that's going to play a nice role. So what is the curl? Del cross f. And that sends a 3D vector valued function to, again, a 3D vector valued function. I emphasize 3D because that's the only time you can take a cross product. Dimension 3. All right, but anyways, we started. Number 1, done. Time to start on the next one. Which brings us to number 2. And it's a picture one. This is gonna be awesome. All right. Select the appropriate C. So you're probably like, C. No, that's not what that means. No. C here is curve. So select the appropriate curve from below. And given that, the integral along the curve 4x plus 3y dx plus x plus 2y minus arctangent y squared dy is 8. Now, as you look at these curves, what's happening here? Well, they're all tracing over the same sort of underlying structure. They're just doing it in slightly different ways. So, for example, A, we move around. Whoops, I went the wrong direction. Move around, then we come up, and then we go around, then we come down. And in B, which way do we go? Well, we're going to go around, over here, over through here, and back down. So we're always tracing out the same underlying thing. The question is, how do we do it? We're slightly changing the directions. And that's indicated here by the arrows. And when you change the directions, well, that's going to change the values. And so the question is, which one is going to be the right value? All right, now let's look at it. What tool are they trying to get us to use? How do we know it? Well, there's a dead giveaway. Notice that they gave us this symbol here. Do you see how there's a little halo around that integral sign? That's telling you something very specific. It's saying, hey, this is a closed curve, right? So when you have a closed curve in the plane, you should always think, oh, Green's theorem. All right, so we say, aha, Green's theorem. Now, what does that say? Well, it says if you have a closed curve, then you have the following. The integral around that closed curve C of m dx plus n dy is equal to the integral over the region of n sub x minus m sub y dA, where the region is the part enclosed by the curve. Now, if you look at what's going on, the curves, again, they're actually all enclosing the same region. They're enclosing 3 rectangles. But hold on, there's more to this story, right? Because orientation matters. Remember, to the left, when you walk the curve, keep the region to your left, right? Yes, orientation matters. Now, what happens if we go and flip orientation? You change the sign. All right, so that's actually what's, at the end of the day, that's what this problem is testing us on, is do we understand orientation and Green's theorem. All right, so let's dig into it a little bit. So I'm going to think about our region. So we have our 3 rectangles. I'm going to draw them a little bit big here. And we have that. And now, and I'll explain what I'm doing here in just a second. I should have first done Green's theorem. So let's do Green's theorem really quick for this very specific case. Here we have our m. Here we have our n. So this becomes the following. 8 is equal to the integral over the region of n sub x. So take derivative with respect to x, and notice this terrible looking thing gone. Minus m sub y. Take the derivative with respect to y. Well, that would be 3 dA. All right, well, that becomes equal to what? Well, negative 2 integral over our region dA. Or we need to have the integral over our region, dA, equals -4. All right. Now, at this point, like, okay, so how do we get that? Because isn't this a total area? We can't have area be negative. This is when orientation matters. All right, so here we go. Let's think about it. If we go, let's say, counterclockwise, right, that's our to the left, how much area is there? Well, we think of it as +2. But if we go clockwise, right, so the opposite direction, that would have -2, right, because you gotta change the sign. And I do apologize, this is very hard to see what I'm writing here. Maybe I'll write it a little bit bigger on the side. Okay, so clockwise +2, counterclockwise -2. All right, we'll just write it there. Okay, now the other ones are a little bit bigger, so it'll be easier for us to fit these in. Now, this piece, you can count, it has area 6. So we have counterclockwise is a +6, and clockwise is a -6. And now we say, okay, our last piece down here is what? Well, it has area 4, and so, okay, counterclockwise, excuse me, 4, counterclockwise, -4. Now, what do we do? How's this going to work? Well, here's the idea. We're going to figure out our orientations by saying we need to pick an orientation for each one of these 3 pieces such that when we put them all together, we get -4. All right, now, this 6 is so big compared to 2 and 4 that if I don't choose the -6, hopeless. Okay, so we know we have the -6. So we have to be traveling in our clockwise direction. Now again, 4 is so dominant, we have to say, well, look, if we go -4, hopeless. So we got to go +4, and then we have hope, right? Because that brings us to -2. That brings us within range. So here, we're going to go counterclockwise. Now, what do we need up here? Well, -6 and 4 makes -2. We need to get to -4, so we need to go clockwise, which says that what directions do we need? Well, we need to be clockwise up here. All right, so we're clockwise on this piece. Here, what do? We also need to be clockwise. All right, so we're clockwise here. And now this 4 says, oh, here we need to be counterclockwise. All right, so that's the orientation. That's how we should move along this curve so that we get the result that we need. All right, so putting it all together, well, what do we have? Which one matches? Let's just check A. Okay, clockwise, good. Clockwise, good. Counterclockwise, good. Oh, it turns out A is the right answer. But you can go through and check, right? Now here, you'll see this part, we don't match. The orientation's wrong, so that's out. Again, orientation wrong there, that's out. Orientation's wrong there, that's out. Okay, here, that orientation is correct. And then you come here and say, oh, but that orientation is wrong, so that's out. So this is the only one which has the right orientation that we need. All right, I will say this is a different flavor of a problem. I actually like this one because it makes you think in a different way. And I love that. I think we need to do more of that. Think outside the box. That's how we get to grow. All right, so 2 down. Now, go to some more straightforward ones, right? Right, hopefully. Number 3, we have the integral from 0 to 1, integral 0 to arc cosine of x, 4/2 minus cosine squared y, dy dx, and we're saying, well, what is it? It's one of these numbers. And our initial reaction is like, okay, Now, this is a classic problem when it comes to multivariable integration. Because you look at this integral and you're like, hopeless, hopeless. And you're like, yeah. So if you see something hopeless, you say, well, wait a second. Idea. Maybe what's going on is they're trying to say, you know what? The problem is we're integrating in the wrong order. We shouldn't integrate dy dx. We should be integrating dx dy. So we're going to switch the order of integration. All right, so if you see our integral and it's like, ugh, this looks terrible, switch order of integration. Okay, so that's our plan. Now, how do we actually get there? Well, we need to understand our region. So we can say things like, well, we understand what y does, and we understand what x does. So we know that x goes from 0 to 1, and y goes from 0 up to arc cosine of x. Now, because I wrote this, I didn't provide a picture, but oftentimes we provide you a picture. We'll see what that looks like. I'll show it to you. Now, a lot of these curves are pretty easy to understand. You say, oh, x equals 0, x equals 1, I understand that. Y equals 0. Yeah, no worries, I understand that. And so then you get to like that last piece, which is like y equals arc cosine x. What? Right? So we have our y equals 0. But think about it this way. If y equals arc cosine of x, that's the inverse cosine. So now take the cosine of both sides, you get x equals cosine of y. So it's like, oh, it's like the cosine function, we just sort of turned it on its side. And so what happens is we get this curve. And so we get from here, and then I will say this is y equals arc cosine x, or x equals arc cosine y. This, by the way, rewriting it in two different forms, like y is function of x and x is function of y, is critical when it comes to setting up a change of order of integration. Okay, now where are we going from? Well, we're going from 0, which is over here, x equals 0, and we're stopping over here at x equals 1. And if you think, what is arc cosine of 1? It's 0. So our region is this piece right here. All right, so that's our region. Good. Progress. Now, what comes next? Well, we're going to change our description. We say, okay, currently we have it dy dx, so we're going to do an integral. The function stays the same. Right, this is not a change the function. We're just changing the order. So that only affects, changing this piece and changing these bounds. So we say, well, what's going on? Where does y go between? Well, we have to figure out, where's this point? All right, that's arc cosine of 0. What angle, when you plug into cosine, gives you 0? The answer may not surprise you. It's pi halves. So we're talking 0 to pi halves. All right, so that's the range for y. So 0 less than or equal to y less than or equal to pi halves. All right, well, think about now a fixed value of y, and where do you go between? Well, you go from 0 on the low end, left low, to right the high. So 0 less than or equal to x, less than or equal to, well, what it was, why did I write x equals arc cosine y? I'm so sorry. Should have written x equals cosine y, up to cosine y. Okay, so that's our bounds here, 0 cosine y. All right, good. Well, good news, we can definitely integrate this with respect to x, because there's no subtleties here. This is all a constant. So we say, okay, great. What do we have? This is integral 0 to pi halves, 4 over 2 minus cosine squared y, x, right, because this is acting like a constant with respect to x, evaluated from x equals 0 to x equals cosine of y, dy. And that becomes what? Well, 0 to pi over 2 of 4 cosine of y over 2 minus cosine squared of y dy. All right, so we've gone down to this integral. And now, what do you do? Well, this is when we get to flex our little bit of Calc 1 knowledge, right? It's good to know Calc 1. It shows up a lot in Calc 2 and 3. So what's our little bit of Calc 1? Well, when in doubt, what do you look for? A substitution. And looking at this, we say, well, is there any hint what kind of substitution to make? Yes, there is a hint. And that is that we see this cosine y. Now you might say, well, why is that a hint? Well, you can look for two things when you're looking for substitutions. A function on the inside, or you say, hey, there's something I recognize as a derivative. Cosine y is a derivative. It's a derivative of sine of y. So idea. If we can write everything in terms of sine, then we can do a substitution. Well, we can. Because what do you have? You have cosine squared y. So you can say, well, look, well, this is really integral 0 to pi halves of 4 cosine y over 2 minus 1 minus sine squared of y dy, right? Because the cosine squared can become a sine squared and vice versa. Or you say, hey, this is like integral 0 to pi halves of 4 cosine of y over 2 minus 1 is 1 plus sine squared of y. All right, now we're cooking. Well, as we said, hey, this is leading us to a substitution. We'll let u equals sine of y. Du can become cosine of y. And dy, say, hey, this becomes integral sine of 0, 0, sine of pi halves, 1. 4 cosine y dy is a du over 1 plus u squared. And that is a familiar integral. Oh, it's a Steve classic. Ho ho! What are the odds? 100%. I mean, this is not the first time we've seen the words arctangent on this exam, right? So this becomes 4 arctangent of u. Evaluate from 0 to 1. Well, arctangent of 0 is 0, and arctangent of 1 is pi over 4. So this is 4 times pi over 4, also known as pi. So our answer is pi, and hey, look, there it is, D. D it is. Now, on a fun side note, I went ahead and plugged this original problem into Wolfram Alpha. What do you think it gave as an answer? Well, it hedged its bet and says 3.14159, but it didn't say pi. Because it did some numerical stuff, so it says, oh yeah, I'm very confident this is what it should be to high precision, but just because I'm close to pi doesn't mean I'm pi. So, hey, good news for us. We can still beat the computer. Woohoo! Yes! And so, we'll have jobs, right? I hope so. I hope so. All right, well, that was a fun problem. Let's keep going now with number 4. Woohoo! Okay. What do we have? Integral 0 to 2 pi, integral 0 to pi over 4, integral 0 to 2, rho squared cosine phi, d rho d phi d theta equals, and then we have a bunch of choices, but notice what do they have? They all have dz dr d theta. So we're like, oh, we recognize these things. These rho phi thetas, what is that telling us? Well, that tells us that we're starting in spherical. And then it says, okay, so we're starting in spherical, but then we're switching it up, and we're going to switch to something with ZR theta. And they all have that. And what does that tell us? Well, that tells us that we're what? We are going to switch to cylindrical. So we're going to go back and forth. All right, between spherical and cylindrical. All right, now that we understand what we're doing, we can start sort of digging into it. What can we say? There's a couple of things. We can talk about bounds, we can talk about function, and we can talk about the dv. And I like to do the dv before I do the function. So let's talk about the dv. Because sometimes you think, oh, this is part of the function. Like, no, it's really part of how you break things up. And so it's take your time. Take your time. All right, so what do we have? Well, for spherical, we have that dv is rho sine of phi d rho d phi d theta. Almost that, but not that. That cosine is not sine. Uh-oh. Uh-oh. Oh. That's going to cause problems. Well, okay, so we'll hold off on that discussion. We say, okay, putting that aside, we also have that dv should be dr, dz, dr, d theta. I almost forgot the r. R. It's the same r that comes from polar coordinates. So we say, okay, so what can we do with this integral? Well, we can think of it in the following way. Integral 0 to 2 pi, integral 0 to pi over 4, integral 0 to 2 of, and then we're going to pull off on the end a rho squared sine phi d rho d phi d theta. Okay? What's left? Well, what haven't we accounted for? We haven't accounted for the cosine, so that's still left. What else have we not accounted for? Well, we haven't accounted for the sine that we put in. So if we put it in, we have to somehow also balance it out. So this is our dv, and we say, okay, that's cool. So that here, this is going to become our r dz dr d theta. But what does cosine phi over sine phi become? Ooh, now that's an interesting question. Let's think about that. Where do we see cosine phi and sine phi? If we pulled out our formula sheet, and I don't have one with me because it's written in my heart, and I hope a lot of it's becoming written in your heart too. It's one of those things that the more you use it, the less you need it. And so hopefully you've been using it so much, you're like, oh, it's ingrained in me. But here's something you'll see. You'll see that there is something that involves cosine phi. And whoops, let me move it down a little bit. It says rho cosine phi is equal to z. All right. And rho sine phi is equal to r. Now, through the miracle of dividing both sides, you get that the rho's cancel, so cosine phi over sine phi is equal to z over r. So you're like, oh. So this part right here is going to become a z over r, which says what? Well, it says if you cancel the r's, what should we be integrating? We should be integrating z dz dr d theta. Well, okay, that's an r. Nope, that's an r. Nope, there's a z, but then there's other stuff, so that's not going to work. R squared over z. Nope. Z dz dr theta. So the answer has to be E, because it's the only one that has the right stuff on the inside. But you know what? Let's just do a little bit more. Let's talk about the bounds, because the bounds don't all match up. So I want to make sure we could also have approached this by saying, what about the bounds? The bounds, the bounds. Okay, well, what's going on? there's something going on here. Notice, what don't you see? Because oftentimes we talk about, oh, what do I see? But what don't you see? What's missing? There's no theta term. What does that tell us? Well, it tells us if there's no theta term, we're spinning. How much are we spinning? Well, we are doing one complete revolution. And the theta for spherical has to match the theta for cylindrical, which you'll notice they all go 0 to 2 pi. But the other thing it says is like, oh, what I can do is I can look at a cross section and spin. So with that mindset, we say, okay, let's look at a cross section. And the way I like to think of it is I like to think of it as the RZ plane. This is our cross section. Here's our Z axis. Here's our R. And once we figured it out, what this does, we can spin. All right, so let's talk about what's going on. We have our phi. Now, we should understand what phi is. Phi is angle off of the positive Z axis. So phi equals 0, straight up. Phi equals pi force, well, that's coming out at a 45-degree angle. So that says we're going in between these two locations. Now, once we have that, we say, okay, between 0 and pi force. So between these two angles, what is rho doing? Well, we see that rho goes from 0 to 2. So 0 is the origin, and 2 is distance 2 away. So rho equals 2 is actually part of a sphere. And so we say, aha, our shape is this part right here. It's like a little tiny slice, like a slice of 1/8 of a circle. And that's because it's a slice of 1/8 of a circle. See how easy it is to figure that out? That's so cool. All right, now with all of that in play, we say cool, and now if you spin it, you get your shape. Now we don't actually need to figure that out, but if we now spin this around, we see that our shape, it's a cone topped by a piece of a sphere. Okay, so that's our shape being described by our bounds. Now let's go and figure out what's going on with our bounds. Well, we have to say, where does R go between? Where does Z go between? So, question, how can we figure out this value here? Well, what do we know? We know this goes out distance 2, so this has length 2. And we know it's a 45, 45, 90 triangle. Okay, with that in mind, let's suppose we call this distance A. A, right? Then we have like A squared plus A squared equals 2 squared, or 2A squared equals 4, or A squared equals 2. So A is square root of 2. So this place is at square root of 2. So R should go from 0 to square root of 2, which knocks out this, this, and that. Right? So we've already knocked out those three. And the last part already matches, but let's go ahead and talk ourselves through it just to make sure we are convinced that we could do this if we saw this on a test. This phi equals pi force, that's going off, in 45 degree or pi force angle. In polar, this is Z equals R. Okay, so the Z starts at R, right? Because for fixed value Z, we go up until we start and move till we hit the sphere. So we start on the line, so we start at R, and then what's this? The sphere? Well, it's part of a circle, and that's the circle with radius 2 in the ZR plane. So that's Z squared plus R squared equals 2 squared. Or, if we solve for z in terms of r, z squared equals 4 minus r squared, or z equals the square root of 4 minus r squared. We need the positive square root because we want the part that's above. And so we are going from r to the square root of 4 minus r squared. And so the bounds also match. But, we didn't actually need that. And that's one of the things. When you're doing these problems, you don't have to justify every single detail. You only need to do enough to say, I know this is the only one that could be correct. So you can strategize, be smart. Oftentimes, a good test taker will bump their grade up by a couple of points. Now, over time, that adds up. So it's not just about learning the material, it's learning how to use it and learning how to be smart. Learning to be a good test taker, that helps. By the way, that skill set does translate. It's like, oh, if I'm a good test taker, it's never going to help me in the future. No, it's being a good test taker is like saying, how can I be efficient? How can I help myself succeed as well as possible given the resources I have? And that's a good thing to do. All right, so that's number 4. All right, good. And I'll say I'm not going for time. I'm going to talk a lot. So you're probably like, oh, Steve, you're not going to finish in time. That's okay. That's all right. Let's go on to number 5. Which of the following functions is conservative? Okay, now let's remind ourselves, what does conservative mean? Well, conservative means the following. It means that you have, now these are all 2-dimensional vectors. So I'm going to put everything in terms of our m comma n. That comes from the gradient of some function xy. Now, how do we show something is conservative? Well, there's 2 ways you can do it. One way is you could find an f, that's strategy 1, so to prove conservative, our strategy session, right? Strategy 1, find f. Strategy 2 says, look, it doesn't actually ask us to find f. Sometimes that's extra work. All we have to do is enough to verify conservative. And that comes from looking at these functions m and n. And in particular, you need to show the following. If m sub y equals n sub x, you have to be conservative. So in some sense, finding f is like you're going up, right? You're integrating. M sub y equals n sub x says, oh, I'm going down, I'm differentiating. And so I would say, if you're trying to actually, if all you're doing is saying yes or no, is it conservative, 2 is the right thing to do. If you have to do something with that potential function, so this little f is what we call the potential function, then you really should just go and find f. And okay, so I'm going to take this strategy number 2. All right, so here we go. I'm going to write down the my and nx. So I'm going to make a little chart here. We have our a, b, c, d, e. All right, and then we have our my and our nx. All right, so we're going to sit down and just quickly go through these. Now, you wouldn't exhaustively do this whole thing, but I'm going to do it for dramatic effect. All right, I'm going to be overacting in just a moment here. And you're probably thinking like, Steve, you were born to overact. I know, it's in my blood. Okay, what can I do? I can't help myself. Okay, so part A, take the derivative of the first slot with respect to y. That goes away. Derivative of 2x with respect to y, to x. Go to the next term, take derivative with respect to x. Derivative of 6xy, well, that's 6y, and that goes away. All right, not looking promising. Well, let's go ahead and finish this up. That's not looking promising for A. Well, it shouldn't look promising for 4 out of 5, because one of them should be conservative. That's the thing with multiple choice. Only one should be correct. All right, now, take the derivative of the first slot with respect to y. the minus x goes away. You get 4 sine squared of x. Take rid of the second slot with respect to x. Y cubed goes away. And you're going to get 2 minus, here, chain rule. Root of sine is cosine. And then you're going to have to put a 2 out in front. So 2 cosine 2x. Okay, let's do C. Take rid of the first term with respect to y. Oh, thank goodness, that was going to look terrible. That's a 1. And then take rid of the second slot with respect to x. And there's nothing, there's no x's there. Okay, D. Get rid of the first slot with respect to y. That's a 4x cubed. Here, we take rid of this with respect to y. What do we get? Oh, well, we get a minus x squared e to the xy, and that goes away. Now come here, take rid of this with respect to x. That's a 4x cubed. Take rid of this with respect to x, and that's a minus y squared e to the xy. And take rid of this with respect to x, and that's a plus 2. And now, okay, last one. Take rid of the first side with respect to y, and that's a 2y over y squared plus 1. Take rid of this with respect to x, that's 2x over x squared plus 1, and there we go. Now, we're just looking for where 2 of these match. They're equal. And what does it look like? It looks like none of them match. Ah! Well, okay. Let's just point out, definitely it's not C, hopeless. And for algebra, there's not a lot you can do with algebra. So here, there's a plus 2. There's no plus 2 there. Forget it. Hopeless. Here, you have x's on one side, y's on the other side. It's not going to work. But notice this one. There's a little sliver of hope. Because what do we have? We have trig. And one of the things about trig that's really cool is there's a lot of ways to rewrite a single expression. One of the challenging things about trig is that there's a lot of ways to rewrite a single expression. You know, so sometimes it's like, wait, are these the same? Are they not the same? It takes a minute to figure it out. So how about this time? Well, if you divide both sides by 4, this becomes sine squared of x. Does that equal, question, 1/2, 1 minus cosine of 2x, right? Because if you divide by 4, 2 over 4 is a half. And we're like, oh, this is a thing. It's a thing. Wow! What is it? This is our power reduction identity. So this is true. Okay, so this in fact is true, which means that these match. So even though initially it looks like they don't match, in fact, you say, we're smart enough, we can pick up and say, hey, these actually do. Now, just on a side note, after I wrote this practice, I did notice, this is a little trig heavy, and I hope you like trig. And if you don't worry. You know, we don't usually put this much trig on in an exam. We'll always put some, right? Some, but probably not this much. Okay, so we've had 5 up to number 6. And it's our last multiple choice. Which of the following integrals will give the flux of the vector field f, which is xy plus z squared minus 3yz xz, through the surface G with upward pointing normals, which is the portion of the plane z equals x plus 2y over the region 0 less than equal to x less than equal to 2 and 0 less than equal to y less than equal to 2. Oh my gosh, there's a lot going on here. And all of this is to say, do you recognize this? So, here's the thing. When we talk about flux through a surface, what we're really talking about is adding up over our surface f dot n dsa. That's what computing the flux is. So you can think of f, and that's saying what? Well, it's recording a direction of movement in some sense and a rate of movement. So it's a rate of flow. And when we dot it within, let's say, well, what's the rate passing through there at this point? And okay, so that's a rate times an area. That's how much flow is happening at a single point. And then we add up, that's the total amount of flow. Okay, so that's the flux. There's a special case. Now, we haven't done a lot of surface integrals, Well, what we can do is say, well, in the case when our surface has a particular form, so it's z equals f of xy, so this x plus 2y, this is our f of x comma y. So f of xy over a region R, so this 0 less than or equal to x less than or equal to 2, 0 less than or equal to y less than or equal to 2. This is our region R. And we have upward pointing normals. And we know we have upward pointing normals because it tells us that we have upward pointing normals. And essentially when we're talking about upward pointing normals, is it saying, let's take a second and let's orient this surface, right? Like, which is the top side? That's the upward side. Okay, because when we talk about flow, you know, there's a plus sign and a minus sign. So we have to think about, well, okay, you know, because you could have parts of the f is going in one direction, parts of f is going the other direction. And so we have to decide which way is positive, which way is negative. That's an orientation. So all of that is to say, if we have upward pointing normals, z equals f of xy over a region R, then, and this is on the formula sheet, so there's no big surprises here, this is equal to the integral over the region R of, and I do apologize, I'm going to write one more thing, f is mnp. You can have minus m fx minus n fy plus p dA. Okay, so what does this problem reduce to? Well, we have to have our dA and integral over r, they all match. So what this problem really is about is to say, hey, what is this? If we know what this is, then that tells us which one of these things is the right answer. All right, so we proceed. Now, one small note. We're going to probably do this in a couple of steps, but one thing to keep in mind is that there's this important fact. Any z that we do come across is going to be replaced by x plus 2y. Okay, so let's go through here carefully. So we're going to do this in a couple of steps. So minus m fx minus n fy plus p is minus, and I'm just going to do it literally right now, xy plus z squared f sub x. So what's the derivative of this function with respect to x? 1 minus n minus 3yz times f sub y. What is f sub y? Derivative of f with respect to y, 2, plus p, which is xz. Okay, now that's none of these because we have to replace the z's. All right, so we'll even make a little note of this so we don't forget what we're doing. So need to get it just in terms of x and y. Only of x and y, so z gets replaced by f of xy. And in our case, we know what f of xy is. It's x plus 2y. Okay, so here we go. This is minus xy plus x plus 2y squared times the 1. Minus minus is a plus, and there's a 2 times 3, so that's a plus 6y, and times z, or z, x plus 2y, plus x times x plus 2y. All right, so that's the expression. Clean it up, clean it up. Okay, no worries, we're getting there, we're getting there. Okay, so here we go. Let's square this. This will become x squared plus the cross terms, 4xy plus 4y squared. And there's an xy as well. So when we put the minus in, so we're going to get minus x squared, that 4xy plus xy, 5xy, so minus 5xy, and minus 4y squared, plus 6xy, plus 12y squared, plus x squared, plus 2xy. Okay, so we start gathering. Okay, well, there's a minus x squared, there's a plus x squared. Gone. Cancel. Nice, nice. Okay, so there's no x squareds left. All right, now, what else do we have? Well, we have a minus 5xy, a plus 6xy, and a 2xy. Well, minus 5 plus 6 plus 2 will give us 3xy. So we're already looking for a 3xy. So there's a couple of them that have 3xy. But this one has an x squared. So we're betting on C. But let's go ahead and check with the y's because we should. Okay, what's happening with the y's? Well, we have a minus 4y squared and a plus 12y squared. And that makes 8y squared. So, what is this? Well, the answer is 3xy plus 8y squared. So that's what we need to be integrating over our region. And so, our answer is C. 3xy plus 8y squared, the integral of our region, which is 0 to 2, 0 to 2. And there we go. Woohoo! Our last multiple choice. Now we get to some fun parts. Long answer. That's right. Show your work. Get the points. Pass the class. You know, all those things. Number 7. Let G be the surface. Z equals a half x squared plus a half y squared, where Z goes from 0 to 3/2. Given that the electrical charge density on the surface, and that is the charge per unit of surface area, is a density, xyz is 1 minus z, find the total electrical charge on the surface G. Now, how should we be thinking of this? Well, you think of density, so it's like, oh, this is kind of like mass. Yes, it's exactly like mass. The only difference here is with electrical charge, you can have positive and negative parts. So this makes it a lot easier for the problem writer because they're like, hey, I can have a density function which is both positive and negative for my object. And that's what happens here. So we say, okay, idea. What's our idea? Well, our total charge is going to be equal to the integral over our surface, our density, dSA. Right? If you want to find mass, you integrate density. You want to find total charge, integrate electric density. Okay. Well, now we say, hey, we know what density is. It's 1 minus z. So this is integral of g of 1 minus z dSA. They say, cool, cool, cool. But how do we do this? All right, so here's how we're going to do this. We say we're going to do the following. We're going to reduce it. Instead of being on the surface, we're going to reduce it to something in the plane. So instead of sitting in a three-dimensional thing, it's in the two-dimensional thing. And that we feel a lot more comfortable in. We have more confidence, and we have a better shot of understanding what's going on. So let's talk about what is this surface and get some intuition. Well, we have z is a half x squared plus a half y squared, and so that should look familiar. What is that? Well, that's a paraboloid. It's a bowl. So it's a bowl that opens up. It's sitting right on the xy plane, and it's opening up. So we have this bowl. So here's our surface G. And we stop it here at z equals 3/2. So, and z equals 0 is the bottom of the bowl. Now, what are we going to do? Well, we're going to try to figure out what is the region it's sitting over, and then we're going to rewrite things in terms of that. So we say, okay, what's going on? Well, if we think about what's going on, we say our region is just imagine looking straight down the z-axis. Like, what does it look like if we look straight down the z-axis? Well, it would look like a circle. Now, which circle would it look like? All right, that's a good question. And here's how we find the answer. The lip of the bowl is going to help us figure it out. So we say, well, that's a half x squared plus a half y squared equals 3. Whoops. Sorry, I'm kind of on the edge there. 3/2, not 3. Or x squared plus y squared equals 3. So that is our region. And so that's just the equals is the edge. So we're in the interior. X squared plus y squared less than or equal to 3. Okay, so here, this is our region R. All right, now here's what's going to happen. We are going to rewrite this integral in terms of R. So this is going to become the integral over R 1 minus z. Now, we want to get down to the xy plane. So what do? Well, we can't have z's left. So what we do is we say, well, hey, we know something about z. It's a half x squared plus a half y squared. So it's going to become z minus, and I'll go ahead and factor out a half, x squared plus y squared. Okay, so that's 1 minus z. Now, what is dsa? Well, I'm glad you asked. So dsa, if we have z equals f of xy, looks like the square root of 1 plus fx squared plus fy squared dA, where we have z equals f of xy. So for us, our f of xy is a half x squared plus half y squared. So if we take the derivative with respect to x, what do we get? X, right? The 2 comes down, we get x. So it becomes 1 plus x squared. Take the derivative with respect to y, we get y. So plus y squared. And there we go. So the dsa part, right? So let's be clear what maps to what. So this 1 minus z maps to here. And then the dsa, that's going to be the square root 1 plus, all right, this says x squared plus y squared dA. And so again, just to emphasize what's mapping to what, the dsa, that becomes that piece. Okay, good. Now, we say we got to integrate this. It didn't say set up an integral to find it. It says find it. So how would we integrate such a thing? Well, there should hopefully be some like bells going off in your head. At this point, you're like, wait a second, hold on. What do we see? Well, we see an x squared plus y squared there. We see an x squared plus y squared there. We see an x squared plus y squared there. This problem is lots of x squared plus y squareds. So what does that tell us? It tells us go to polar. So we're going to go to polar. Okay, so here we go. For our region, well, it's the circle of radius root 3. It's the whole circle. So in terms of theta, well, let's not get ahead of ourselves. Let's go ahead and do our function. 1 minus 1/2 r squared square root 1 plus r squared. And then we have our dA, which is r dr d theta. And what can we say about theta? Full circle, 0 to 2 pi. And then where does r go from? Well, it goes from 0 to the edge of the circle, 0 to root 3. All right. Now, at this point, you're probably like, ugh, is this even integrable? This is not looking good, Steve. I thought you said we could do this one. We can. Have faith, my young friends. Have faith. We will succeed. Our powers combined, we can do this integral. So, let's make a quick observation. Notice there's no theta in the middle. So, we can just do the outside integral separately. What's the integral from 0 to 2 pi of d theta? 2 pi, right? You'll see this a lot. So it's okay to say, like, okay, I just see the 2 pi, boom, done. Don't forget it. You can account for it, but it can save you a step. Okay, so we have 2 pi. So this comes from the integral of d theta. So from the d theta integral. Now, how would you do the next integral? Well, it's not looking great, but then you say, you know what? I don't like the square root of 1 plus r squared. I see something on the inside. You're like, well, wait a second. If I see something on the inside, that suggests I should try substitution. Substitution is an inside job. So we're going to do that. So you say, okay, let's do a substitution. We'll let u equal 1 plus r squared. What would du be? Well, it would be 2r dr. Or, using advanced marker technology, 1/2 du is r dr. And notice, what do you have? An r dr. Okay, so that's good. But you say, well, what about that part? Well, what do we know? U is 1 plus r squared, so r squared is u minus 1. So we can update. Now, we'll update our bounds. These are r bounds. R equals 0. What does u equal? 1. Right? 0 squared plus 1. R equals root 3. What does u equal? Well, root 3 squared is 3 plus 1 is 4. Then we get 1 minus 1/2 times u minus 1. Okay, so that's this piece. Square root of u. And then we have a 1/2 du. And this is going to be something we can integrate. All right, so we do some little cleaning up. A little bit here, a little bit there. So, for example, if we distribute, this would be minus 1/2 times minus 1 is 1/2, plus 1 makes 3/2, minus 1/2 u. And we already have a half. Well, let's go ahead and use that to cancel with the 2 in the pi. And square root of u, in a calculus-friendly way, we would write that as u to the 1/2. So, what do we have? We have the following. This is equal to, trying to pick a good color here. Color theory, right? It makes all the difference. We have a pi, because we've got 2.5 to cancel, and then we haven't done the integral yet, so integral 1 to 4 of 3/2 u to the 1/2 minus 1/2 u to the 3/2 du. And we're almost there. We're so close. So this is pi. Well, when we integrate, we get 3 halves. We'll have u to the 3 halves, and then multiply by the reciprocal, which is 2/3, minus 1 half, u to the 5 halves, multiplied by the reciprocal of 2/5. All right, the 2/3 and the 3 halves cancels. Here the 2's cancel, and we're evaluating 1 to 4. All right, so we have, and again, we can go through, and okay, so we'll have, this is pi, u to the 3 halves, minus 1/5 u to the 5 halves, from 1 to 4. Okay, so we're almost there. We plug in, and we're done. All right, so plugging in. 4 to the 3 halves. Well, take the square root of 4, right? Because the 3 makes it big, the square root makes it small. So do the small, then do big. Smaller than bigger is easier than bigger than smaller. Okay, so square root of 4 is 2. 2 cubed is 8. So we have pi 8. All right, 4 to the 5 halves. Okay, so square root of 4 is 2. 2 to the 5th is 32. So minus 32/5. Subtract. Plug in 1. Well, that's going to be pretty straightforward. When you plug in 1, you just get the coefficient in front. So it's going to be 1 minus 1/5. Okay, so this is pi. And let's go ahead and put everything over a 5. So that's 40 over 5, minus 32 over 5, minus 1, which is minus 5 over 5, and plus 1 over 5. And so we just have to add these up. So we have 40 minus 32 is 8, minus 5 is 3, plus 1 makes 4. So pi times 4/5. 4/5 pi. And there we go. Ah, wow. That was actually a surprisingly nice answer, right? You thought it was going to be a terrible answer. But I think 4/5 pi, that's beautiful. Beautiful. And it's something we can do. This is in our wheelhouse. These are things we are capable of doing. And it's also something, depending upon where you go, say you want to be an electrical engineer, this is something you want to be able to do, because you will see this kind of problem again. All right, well, enough romanticizing about number 7. We move on to number 8. Let r of t equal, so r of t, usually when you see that, it's a parametric curve. And you can even see it. We have 0 to 1, it's a parameterization. That's a hard word. Why do they have to make words so long of a curve C? And looking at this, this looks, yes, it looks terrible. I don't disagree with you. So it's an ugly curve. So that's actually a clue. But let's go keep reading. We're going to find the integral along the curve of 3x squared y plus 2xz squared minus 3x squared x cubed plus 2z squared and 2x squared z plus 4yz plus pi sine pi z dot dr. And what's going on here? Well, dot dr, this, by the way, is another way to write dot t ds. It's another way for us to write m dx plus n dy plus p dz. So, when we see an unpleasant curve, or maybe we won't even see a curve at all, they'll just say, well, C is some curve that starts here and ends here. So when we see an unpleasant curve or an unspecified curve, that's a clue that it's not really the curve that matters. Well, a little bit of it matters. And so the little bit will be the endpoints. But ugly curve says, and I hate to write the word ugly. All curves have beauty. But ugly curve, well, that makes us think, try our fundamental theorem of calculus for line integrals. So what is that? Well, we are thinking that this function is not just a random function. It's not something that just walked in off the street. It actually came from someplace. And that someplace is saying what? We think this is a conservative function. All right, with that in mind, we say, okay, let's try to find a potential. So try to find a potential. Now, if we fail, we reset and say, well, let's think of what we can do. But oftentimes, when we have a problem phrased to us in this way, it says, oh, this is likely a conservative line integral. Line integrals of conservative functions are easy if you can find the potential. Now, what's going on? Well, when we talk about finding a potential, we're looking for a function f of x, y, z. And we have three pieces of it. In essence, we're saying this part right here should be our f sub x, while the piece next to it, this part right here, this should be our f sub y, and then the last part of it, well, that part should be our f of z. So we are told these are some derivatives. Can you piece them together? So here's how I do it, and I think it works pretty well, especially if you know it's going to work. You say, well, hey, I can find f by integrating f sub x dx. So we're going to integrate this first part with respect to x. We say, all right, well, integral here, that's x cubed y. So we're treating the x as variable, everything else is constant, plus x squared z squared minus x cubed. Then there's a constant, and that's constant with respect to x, so it's anything which only involves y and z. We do the same thing with the other slots. We say, okay, if I want to look what f looks like, I integrate f sub y. Okay, well here I'm treating anything that doesn't involve y as a constant. And you look, well, everything's a constant here. Well, okay, that can happen. That's okay. So what do we get? Well, we get an x cubed y and a 2z squared y plus anything that doesn't depend on y. And then we go to our last one. So, okay, our f sub z. So f is the integral of f z dz. So integrate with respect to z. Integral of 2z is z squared, so that would make a x squared z squared. Integral of 4z is 2z squared, so that would give us a 2z squared y. And integral of pi, sine of pi z, well, what's the integral of sine? Negative cosine, right? Yeah. Then the pi's, well, yeah, the pi in front will cancel out because you have to be careful with the chain rule. So minus cosine pi z. And then, of course, something which depends only on x and y. Okay, so we have that f has to look like these things. And now we say, let's put them all together. So we have to check for consistency. And by consistency, I say anything which involves multiple variables has to show up in all the places which involve those particular variables. So like this x cubed y, which was part of the x, also has to show up in the part with the y. So that's a consistency check. That's good. The x squared z squared, okay, that has to show up both in the x part and the z part. Good. The 2z squared y, that has to show up in both the y part and the z part, which is good. And then you have the other pieces. You have the minus x cubed. That only has to be in the part with the x, so there's really not much you have to check for consistency. And this minus cosine pi z, that just has to be in the part with the z. Okay, so consistency check was passed. How do we get our function then? Well, by putting it all together, we get f equals the x cubed y, the x squared z squared, the 2z squared y, the minus x cubed, and the minus cosine pi z. Now, this is not the only only f. Actually, there's definitely many potential functions, but all other potential functions will look like this, plus a constant c. So that's the potential. Now we say, cool, we've done most of the work to solve this problem, but not all of it. What else needs to be done? Well, the other thing that needs to be done is we have to say, okay, what's going on with our curve C? And so we'll do a little side note. We'll say what's happening at C of 0, which is the start, and what's happening at C of 1, which is the end. So we need to know those places. So what do? You literally just plug 0 in. So we have 2 times 0, which is 0. Oh, we don't need to write that. We'll have e to the 0 minus 0. So that's e to the 0. E to the 0 is 1. And so we have minus 1. Cosine of pi times 0 is a 1. Sine of pi is 0. So we get a 1. Arctangent of 0 is 0. So times that by 4 over pi, you still get 0. So we're at minus 1, positive 1, and 0. All right. That's when we plug in 0. Now, let's plug in 1. What happens? Well, here, we're going to get 2 times 1, which is 2. Then we're going to e to the 1 minus 1. That's e to the 0, which is 1. 2 minus 1 plus 1. Cosine of pi is minus 1. But sine of pi is 0, so that goes away. Arctangent of 1, that's pi over 4. Pi over 4 times 4 over pi is 1. So we start at minus 1, 1, 0. We end at 1, minus 1, 1. Aha! In other words, there's a term for this in math, nice. And we like nice things. We deserve nice things. We're nice people, right? Of course you are. Of course you are. And we want to give you fun, interesting problems. All right, now, with all this in mind, it doesn't hurt to double check, make sure you evaluate things correctly. And so that's why I'm sort of humming and hawing for a second as I stare. But yeah, we're looking great. So, the final step. So our answer is done by the following. We take our potential function, x cubed y plus x squared z squared plus 2z squared y minus x cubed minus cosine pi z, and we evaluate from the start. So that's going to be a point minus 1, 1, 0 to the end. 1, minus 1, 1. Okay, so make sure you know which one's the start, which one's the end. So it's plug in the end, subtract, plug in the start. All right, so here we go. This is a place where it's easy to make mistakes, so take your time, and let's find out what happens. So we take 1 cubed times minus 1. So that's a minus 1. 1 squared times 1 squared. That's a plus 1. Then we have plus 2 times 1 squared times minus 1. Right? 2z squared y. So that is going to be a minus 2. Then we're going to subtract 1 cubed. So that's a minus 1. Then we're going to subtract a cosine of pi. Well, what is cosine of pi? Cosine of pi is minus 1. So we're subtracting minus 1, which becomes a plus 1. Okay, so that's what happens when we plug in 1, minus 1, 1. Now, some good news. We could use some good news. Those cancel. And also, these cancel. Nice. So it becomes minus 2. In the first thought, that's what's left. But don't forget we're subtracting. Now we're going to go through and do this again. Minus 1 cubed times 1 is a minus 1. Minus 1 squared times 0 is 0. 2 times 0 squared times 1 is 0. Then we're going to subtract minus 1 cubed. Well, minus 1 cubed is minus 1. Subtracting that makes that a plus 1. And then we're going to subtract a cosine of 0. What's cosine of 0? Minus 1. All right, well, cosine of 0 is 1, but we're subtracting it, so minus 1. Okay, so zeros go away, and 1 minus 1 is 0. So this becomes minus 2 plus 1, or minus 1. Ah, good. A lot of work to get to a minus 1, but, you know, it's the process. The process. That's what we're testing on. So you want to make sure you get the processes down correctly. All right, that brings us up to number 9. Okay. Rewrite the following as a single integral by changing the order of integration to dy, dx, dz. So what do we have? We are looking for one integral to rule them all, one integral to find them, one integral to bring them all, and in the light of multivariable calculus, bind them. Right? Yes, that's what we're going to do. Okay, so let's do it. All right, well, now how do we start? Let's start by talking about what's going on. Now, the functions is the same for both pieces, right? That's why we have a hope to rewrite this e to the xyz. And by the way, e to the xyz is going to be hopeless to integrate. Don't even try. It's just like, forget about it. It's not happening. It's an unpleasant thing to integrate. It's a different story, but okay. But we don't have to integrate this, right? This is about rewriting. In many respects, this test is going to test us more on do we understand how to set things up? Do you understand how to rewrite things? Than it is trying to test us on, hey, do you know these obscure little facts? No. It's not. It's like, do you know the basics? Okay. All right. So let's start with our first piece. Well, we pair things up and we see what's going on. So the outer layer says -1 less than or equal to y less than or equal to 0. Then the next layer says that -y less than or equal to z less than or equal to 1. And the last, or innermost, maybe is how we should say it, is that x goes 0 to 1. Okay, so remember we have numbers, curves, and surfaces when we talk about setting up our bounds from the inside out, right? So the innermost layer is surfaces. So one thing that we can do to try to help us sort of get an intuition about what's going on is to say, well, if we just start with these pieces here, well, what do we have? We have the following, and we can draw it in the YZ plane. So here we have the YZ plane. We're told that we go from -1 to 0 for y, and then we have what? Well, we get z is less than or equal to 1. Okay, so z equals 1 is up here. And then we're said z equals minus y. Well, what does that look like? Well, it starts at 1 for -1, and it's going down. So it's this triangle. So that's what the outer two layers are telling us. It's this triangle. Now, what happens when we go to 3 dimensions? Well, when we add our third dimension is x. And actually, it fits in, slots in really nicely. And we're going from x equals 0, which is this part right here, and we're going to just move straight across to x equals 1. And so what we have is essentially we have like a wedge. So here, this face right here is x equals 1. This back face here is x equals 0. So we have this triangular wedge. So that's that integral. We're going to do the same thing with this integral next. Okay, so again, we just pair up. Okay, so we have our layers. So if we go from our outermost layer, 0 less than or equal to x less than or equal to 1, then we have 0 less than or equal to y less than or equal to 1 minus x squared, and then we have 0 less than or equal to z less than or equal to 1. All right, now what's going on here? Well, we can start down, the outer two layers of the xy plane. So if we just do that again, so we have our xy plane, and we're told that x goes 0 to 1. Well, what does y do? We go from 0 to 1 minus x squared. So 1 minus x squared is this parabola. And so in the xy plane, we say, oh, hey, we have this shape here. Now, what's happening? Well, we're going to add in the third dimension. And in our case, the third dimension is z. So that's coming in through here. So here is z. And where are we going? Well, we're going from z equals 0. That's down here. Then we're just going to copy it straight across, right? Because z equals 1 is this plane. It's just going straight up and down. And so it's sort of like, almost like, again, it's like a wedge, but instead of being a triangular wedge, it's this parabolic wedge. And you say, oh, okay, all right, good. Now, what do you notice about these two shapes? Well, they're going to fit together really nicely. Do you see how there's a square right here sitting right on top of the xz plane? It matches with this square right there. So when we put these two together, what do we get? Well, their shapes combined, we get the following. We have this square. I'm going to draw the square in explicitly just to help us understand what's going on. And on the back side, right, which is for the negative values of y, we are coming off into this triangular wedge. And then for the front side, we're spinning in a slightly different direction. So it's a parabolic wedge. And that's our shape. Well, if we were to put the two of them together, which is what we're trying to do. Okay, so we're ready now. We're ready. Okay, so here we go. We're going to get the following. Well, let's talk about it. We have dy, dx, dz. So we need to have, to have z. We need to go that between numbers. We have to have our x goes between curves. And we have to have that our y is going to go between surfaces. Okay? So, here's the thing. When we look down the y-axis, we see this square. We say, oh, a square is really easy to describe. In terms of z, we're going from 0 to 1. In terms of x, we're also going 0 to 1. Now, where does y go from? Well, y is going to go in between this slanted face on the back up to this curved face in the front. So, what's our slanted face? On the back, that's the face z equals minus y, or y equals minus z. So that's minus z less than or equal to y. On the front, what's that? Well, that's y equals 1 minus x squared. So that says, okay, we go from minus z up to 1 minus x squared. So I ran out of space there. I'll rewrite it, minus z less than or equal to y, less than or equal to 1 minus x squared. And we're done. We have our description. What does it mean when we talk about setting up bounds for integrals? It really means describing the region in this systematic way. Between what two numbers, between what two curves, between what two surfaces. Because once you have that set up, you just write it down. So we get integral, 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 same function. And we're going in the order dy, dx, dz. So we go 0, 1, 0, 1. Right? Well, z goes 0 to 1. X goes 0 to 1. And keep in mind, when we talk about x going 0 to 1, it's not number to number. It's the function 0, the function 1. And then y goes from minus z up to 1 minus x squared. And we're done. That's the goal. Woohoo! Nice. Nice. This is a fun one. It's just sort of like, can you visualize things? And I think that's an important tool. It's an important thing like, can you think geometrically? That's the challenge of this test and of this course is, can you think geometrically? And I think you can. I think you can. All right, well, that was number 9, which means one last problem. Our final problem, number 10. Woohoo! 10, 10, 10, 10. Use the change of variables u equals y minus x and v equals y minus x squared to evaluate the integral. Integral 1 to 2, integral x squared to x plus 2, 4x minus 2 over 1 plus y minus x quantity squared dy dx. I will say it's possible to do this without a change of variables, but not pleasant, and it requires a little bit of calculus 2 knowledge. We'll see at the end that you don't need calculus 2 knowledge to do this integral. If you carry it out, the setup correctly, of course. Now, what kind of problem is this? Change of variables. What gives it away? Well, because it says change of variables, that's a very strong clue. But there's other things going on here. You know, it's like, hey, they gave us a u equals, v equals, and that's a very good clue. Now, when it comes to change of variables, there's an important formula on the formula sheet, and it says the following. It says du dv is equal to u sub x, u sub y, vx, vy, dx, dy. And so we're going to need that. So what's going to happen? Well, every integral has 3 important aspects. And so whenever you think about doing something to an integral, all of those has to be accounted for. What are they? Well, you have the bounds, you have the function, but then you have this breaking things into little pieces, right? The measuring of the area of your little pieces. You know, what does that mean? You know, how do you accomplish that? And this is that measurement. All right, so with all of this in play, we're going to go through and say we have to check 3 things. We should always start with the Jacobian and say, let's think about the Jacobian. how do we measure, our pieces? How do we make our change? After we do that, then we talk about function, because those are connected, and then we talk about bounds. Then we throw it all together, and we have a new integral, and hopefully a better integral. So we'll start here. We'll go straight from the formula sheet. We say, all right, formula sheet, you know a lot. So what do you tell us? Well, we say, look, du dv is, and we're going to take the absolute value. That's, important. It's not just anything, it's absolute value. And we start taking our derivatives. U sub x minus 1. And u sub y, 1. V sub x minus 2x. And v sub y, 1. Okay. dx dy. All right, well, that becomes absolute value of minus 1. And then, right, because we're taking determinant, so down here, up through here. And then plus 2x. Now the question is, what do we know about 2x minus 1? Well, x is going to go from 1 to 2. So the smallest that 2x minus 1 could be is 1. So we can drop the absolute value. So this is 2x minus 1 dx dy. All right. So that's useful. Now, how do we use it? We say, hey, is there a 2x minus 1 floating over here? Well, almost. What we can do is we can replace this 4x minus 2 by factoring out a 2 times a 2x minus 1. And then we're like, whoa, hold on a second. This part right here, this 2x minus 1, we're going to attach to dy dx. And that is going to become our du dv. So here, this will become du dv. Which means what? Well, it says that this other stuff here, this becomes our function of u and v. So that's why I want to do the Jacobian first, because something might pull off. And if it pulls off, well, it changes the way we handle the function. Okay, so now we're to our function phase. You say, all right, now we've taken care of our Jacobian phase. Our function phase is almost always quick. I don't want to say it's automatic, but it usually is almost automatic. We say, well, how can we rewrite this in terms of u and v? We say, well, gosh, I see a y minus x, and I see a y minus x. Oh, well, that means that becomes a u squared. And I know what you're thinking. Steve wants us to do one more arctangent. Or does he? What? Ooh, it's going to get interesting, isn't it? Okay, so anyways, that's our function. Okay, good. Okay, so this is our new function. All right. Now, the bounds. Don't forget the bounds. Okay, so how do you do the bounds? Well, start by the current bounds. We know that x goes 1 to 2. And y goes x squared to x plus 2. So you do a quick sketch. Yeah, I know. Like I say, you have to be a little bit sketchy on this exam. Drawing a picture, you should expect to draw a picture at some point. But we're going to keep them pretty simple. Nothing very exotic. So be prepared. Don't be nervous. Don't be worried. Don't be scared. Be prepared. All right, so we have x equals 1. And we have x equals 2. All right, we'll say that's 1 and 2. Y equals x squared. Now, here what you can do is just do something very simple. Say, let's think about what's going on. At 1, we're at 1. And at 2, we're at 4. And we're going up. Okay, so this is y equals x squared. Now, what about x plus 2? Well, at 1, we're 3. And at 2, we're 4 again. So we're there. And so our region, it's a triangle. And this happens a non-zero number of times. It actually happens rather frequently, to be honest with you. But what we're really trying to say here is, hey, can we figure out what are the bounding curves? So here we have 3 bounding curves. What are they? Well, they are x equals 1. We have that one. We have y equals x squared. And we have our y equals x plus 2. Now, here's what's going to happen. These are curves. We want to rewrite them in terms of u and v. So we look for ways to manipulate the expressions so we get things that look like u and v. So let's look at this middle one first, because I think there's an easy manipulation there. If you were to subtract the x squared, this becomes y minus x squared equals 0. But what is y minus x squared? Y minus x squared is v. So it becomes v equals 0. So that's a new bounding curve. How about this y equals x plus 2? Well, again, you see at y minus x, you say, oh, well, this is y minus x equals 2. And y minus x is u. So you get u equals 2. So that's another new boundary curve. And now the x equals 1. Well, not a lot, because both expressions involve x and y. So one thing you can do is, when in doubt, just plug it in this x equals 1, this relationship. You get that u equals y minus 1, and you get v equals y minus 1. Well, if u is y minus 1 and v is y minus 1, what does that tell us? It tells us u equals v. Okay, all right, good. So here we had our, these are the OG, the original bounding curves, and then we have our new bounding curves. So these are the ones that will bound our region in the UV plane. Okay, so we're ready to put almost all of this together. Well, I shouldn't say almost all this, all of this. We're ready. We're ready. Okay, so one last thing before we put it in and finish the problem over here. I do want to sketch this in the UV plane. So this is our XY plane. So in the UV plane, what do we have? Well, V equals 0. That's our U-axis. So that's V equals 0. Our U equals V. That's pretty easy. And our U equals 2. Looks like that. So we, again, it turned out to be another triangle. Nice. Okay. So here we go. Here we go. We are now going to integrate this. So we have our new function is 2 over 1 plus u squared. So we're going to have integral 2 over 1 plus u squared. But now the question, do we want to do du dv or dv du? Because we can pick. And maybe you're not sure. So let's do both of them, and then we'll make up our minds which one we want to finish. We'll start with both of them. Integral 2 over 1 plus u squared dv du. Well, let's start here, the bottom one. Where does u go from? U goes from 0 to 2. And then v goes from 0 to u. Up here, what happens? Where does v go from? V goes from 0 up to also 2. So it's still 0 to 2. And where do we go from? Well, we go from our u equals v. So we go from v all the way over to 2. Okay, so do you see which one is the easier one yet? Maybe it's not so clear. I will say, spoiler alert, I have a bias. Actually, I'm going to go ahead and tell you. It's the second one. It's the bottom one. But we'll go a little bit further before we say, oh, what do we do? What's nice about the bottom one? There's two nice features about the bottom one. One is that we have more zeros, and we like 0. 0 is a friend of ours. The other thing is here, the integral, there's no v's involved. But here there are u's involved. And so oftentimes if the integral says, oh, you say, oh, if I have everything as a function of u, I'd first integrate with respect to v. Everything's in terms of v, oh, I first integrate with respect to u. Okay, so let's proceed. In this first integral, we'd have integral 0 to 2, and then we'd have, well, the integral 1 over 1 plus u squared is arctangent. So that's why you're like, oh, Steve was going to go for arctangent. Evaluate from u equals v to u equals 2 dv. And then this becomes integral 0 to 2 of 2 arctangent of 2, which is a choice, minus 2 arctangent of v. And then you say, oh, I've got to integrate arctangent of v. And can you? You can. What tool do you need? Integration by parts. And, oh, do we remember how that works? This is not looking good. Let's jump ship and try the other one. Okay, so let's do the other one. What happens? Well, this becomes integral 0 to 2. And we say, well, this is going to become 2 over 1 plus u squared v. Evaluate from v equals 0 to v equals u, du. This will be integral 0 to 2. When you plug in 0, you get 0. Remember, 0, friend. When you plug in v equals u, we get 2u over 1 plus u squared. Now that's not arctangent. What is it? It is something we can integrate. If you think about what's the derivative of 1 plus u squared, it's 2u. So you have function downstairs, derivative upstairs. This is natural log of 1 plus u squared, evaluated from 0 to 2. Well, if you plug in u equals 2, 1 plus 2 squared is 5. Natural log of 5. Plug in 0, 1 plus 0 is 1. Natural log of 1 is 0. And so we're done. The answer is the natural log of 5. All right, and there you go. We did it. We did a change of variables, and we evaluated the integral. Oh, we survived. Thank you so much for joining. I hope this helps. Don't get nervous about how fast I went. These problems are slightly harder. I said a lot. I went slow. You're young. You can do this. Get in the practice. Develop your intuition. Develop your knowledge. You'll succeed. Keep at it. You can do this. I know it's a challenge, but what you gain by going through and learning this will help you in what's to come down the road. Remember, if nothing else, you're learning how to think, and that's a highly valuable thing. All right, well, thanks for joining me. I hope you do well, and good luck. See you again. Bye.